Everyone. Sorry again about the technical issues we had today. I just want to go over some math and start doing 3D equilibrium. It's very similar to 2D equilibrium, but worth going over, so I thought I'd do a little screencast. Let's do a little warm-up. So how do you find the length of AB? So how do you find the length of this? Oops, how do I find my pen? Oops, yikes. Let's try that again. How do I find this length here? Well, if we know the point A, which is 0, 6, 2.5, and the point B, which is -2, 0, and 4, and if you can't see that, let's just go through it slow. So A, in the x direction, A is at 0. In the y direction, A is at 6. And then in the z direction, A is at 2.5 feet. And B is at -2 in the x, 0 in the y, it's along that x-axis there, and 4 in the z direction. So what's the length of AB? Well, we have to find that vector AB first, and then the length is just defined as the sum of the squares. So AB is just B minus A. So for each term, take B, take the term of B, subtract off the term from A. So x is -2 minus 0 in the I, y is 0 minus 6 in the j, and z is 4 minus 2.5 in the k. So the vector AB is -2i minus 6j plus 1.5k. All right, so now what is the length? Well, take the sum of the square root of the sum of the square of each term. So nothing to it. Take the square root of -2 squared plus -6 squared plus 1.5 squared, and we get the length is 6.5 feet. So now some definitions. So position vectors are vectors that define the path between 2 points. So vector AB, if we put an arrow on that, points from A to B, and we just define that. So that's vector AB right there. So that could be an R vector. That's just between 2 points. So yeah, what does that vector look like? It has magnitude, it has direction, it's a vector. The length is just the magnitude of R given by the square root of the sum of the squares of the x, y, and j, x, y, and z magnitudes. So we saw the example of that. And then a unit vector is just, you take your vector, AB, and you divide it by its length. And so now you have just a vector of length 1 in the direction of AB. So yeah, very useful because it just points, it's just sort of a pointer. And it has a length of 1, very important, length of 1. All right, cool. So now let's use this. Let's do some statics. Let's figure out what the forces are in this system. If we have this crate right here, which has some weight to it, what's that acting in? If you said -k direction or -1k, you're right. It's just hanging down. So gravity usually acts in the -k direction. So yeah, that weight is in the -k. All right, so let's do it. So if we care about the forces in here, in AB, we have our unit vector, UAB, and we multiply it times whatever force that is, because the force acts in the direction of that cable. Cool. So F of AB is a force in the direction of AB. So if we know A is at 0, 6, 2.5, and B is at -2, 0, and 4, just from before, A of B is the vector we just talked about. That is that full length from A to B. U of A to B is this unit vector, this short unit vector. So the force acts in that direction of A to B, but it doesn't have that magnitude AB. It has the magnitude force in the A to B direction, and its direction is defined by the unit vector, UAB. So FAB is the magnitude. Notice how FAB doesn't have the arrow. That's the magnitude of FAB times the unit vector. So FAB, So if it was 50 pounds, that would be 50 pounds times minus 2 over 6.5, plus 50 pounds times minus 6 over 6.5 in the J, plus 50 pounds times 1.5 over 6.5 in the K. So yeah, the force, its quantity is a magnitude, and its direction is defined by that unit vector. Cool, let's use that. All right, so how do we use it? Well, we use our same equations. The sum of the forces in the X, the sum of the forces in the Y, and the sum of the forces in the Z is 0. And we'll talk about moments a little more on Tuesday. We can still break vectors into their components and make sure that the statics equations are still satisfied. This is how we make our lives easier. We can also visualize ourselves. We can visualize it. So if I look from the Z-axis, what does this look like? Well, from our Z-axis, we have AD going out. So that's A, that's D, and that's right along the Y-axis here. And then we have AB and AC. So if we look from the Z-axis, we can see that, oh, and then our weight goes straight down. We see that in the X direction, the only forces that counteract each other, so the only force that counteracts AB's X direction force is AC's X direction force. So we can probably, if we care about which of these is going to break first, we can probably isolate f of x equals 0. All right, sweet. So if we start visualizing, we can break into components, and we can use the equations that that help us out, that isolate our variables. So we had that question, how do I know which equations to use? Use the ones that isolate the variables you care about. So it's driven by the question. So what I just said, if you look directly above from the Z, draw what you see. Then draw from the right side. So I already did the Z-axis. So if I'm looking from the right side, what does that look like? Well, I got AD, looks like it goes straight up. And then that would be D, that would be A. And that would be, I think, B, like that. And then C goes a little higher. And that's Z, that's X. And I can, again, see that the only components, oh, now we have our weight. I always forget our weight. The only components acting in the X direction come from AB and AC. Cool. And if we can visualize it, great. And if we can't, no big deal. We can use math. So if we can visualize it, great. But if not, we can always use math. And the math that we're going to be using are those equations that we've talked about at length in this class. All right. The hardest part about this problem is bookkeeping. It's really easy to get kind of turned around. So go slow, be rested, and check your work. So oftentimes I see 5.5, and that's related to the Z-axis, but see how it kind of points near the X? I've been known to make that mistake. So be careful, check your work. All right, so let's do it. So if we had the question, which cable would break first? Which cable has more force? So that assumes that the cables are the same cross-section, they're made of the same materials. Yeah, if you can think of an extra assumption, that's cool too. All right, so what is FAB? The force in AB is the magnitude of the force in AB times that direction. And we said the direction vector was minus 2 over 6.5, minus 6 over 6.5, and 1.5 over 6.5. So now, if we care about cables, what is the force acting in the AC direction? Well, it's the magnitude of FAC times that direction vector UAC. So if we know AC, so now AC is this whole length there from A to C. It's 2 minus 0 in the I, 2 minus 0 in the I, 0 minus 6, so C's at 0 in the Y, minus a positive 6 in the J, or in the Y, oops. And then in the Z direction, this is 5.5 minus 2.5 for A. So 5.5 for C, minus 2.5 for A in the K direction. So again, in the y direction, C is at 0 in the y. It's on the xz plane. And A is at 6, 0 minus 6. All right, so what's the magnitude AC? We take the sum of the squares, take the square root. Sum of the squares is 49, square root of 49 is 7. So then FAC vector is the magnitude of FAC times the unit vector in the AC direction. All right, and while we're at it, yeah, why don't we just take AD? So again, we always want to assume that our forces are in tension. So that's going to act to pull that point A. So FAD, we do our analysis. FAD is 0 in the I, minus 6 over 6.5 in the J, minus 2.5 over 6.5 in the K, multiplied by the magnitude of the force, FAD. And if you want, I'll give you the work, how we found the length and how we actually found that vector. And you can pause it if you want, just to make sure you follow along. All right. So now, which cable is going to break for us? Which equations do we use? So FAB, we know is this. FAC, we determined was that. FAD, we determined was this. And we can actually say W acts 0 in the I plus 0 in the J minus 1 in the K. Why is that? Because just the force of gravity, it's pulling it down. All right, so now, which of these equations, f of x, some of the forces in the x, some of the forces in the y, or some of the forces in the z, do we want to use? Well, which component is only acted on by the cables? Well, W has 0 in the I. F of AD has 0 in the I. So F of AB has an I component, and F of AC has an I component. Therefore, if we do the sum of the forces in the x direction, our math says what our visualization said earlier. We can isolate, we can put FAC in terms of FAB. When we do that out, we can tell which one's bigger or smaller. All right, so what equation isolates the cables? That x direction. Only the cables act in the x direction. So sum of the forces in the x direction, it's minus 2 times 6.5, or minus 2 divided by 6.5 times the force FAB, the magnitude FAB. And then our component from FAC is 2 divided by 7 times FAC. We set that equal to 0. We do some algebra. FAB is FAC times 2/7 times 6.5 divided by 2. We move the negative FAB over to the other side. Then we multiply by 6.5 divided by 2. And we see that FAB is FAC times 6.5 divided by 7. The magnitude of FAB is FAC times 6.5 divided by 7, which is less than 1. So we know FAB is less than FAC, so which cable has more force? AC. AC has more force. This analysis just showed it. So which cable is going to break for us? Well, if they're the same kind of cable, same cross section, we assume AC breaks first. All right. So now, if we know when our cables fail, if we can test that, if our cables fail at 300 pounds, how much weight can we load on this thing? Same assumptions from before. Cables are made of the same. Maybe we have an additional assumption that the cables fail before AD does. Yeah, that's made of steel. Maybe the cables are made of fishing line. I don't know. But we can assume that. We also can assume that FAC, if the cables are going to fail first, FAC is 300 pounds. Why? Well, from our previous assumption, we just showed FAC is greater than FAB. It's going to reach 300 pounds first. So we know FAB is our magnitude FAB. We don't know FAB yet. We know FAC is 300 times the direction u vector AC. We know FAD is our magnitude FAD. We don't know that yet, but we know that u vector acts along our component AD. And we know our weight. We don't know the weight yet. We got to find that out. But we do know FAB is FAC times 6.5 over 7. That's the magnitude of FAB is the magnitude of FAC times 6.5 over 7. We just found that out on the last slide. So we know the magnitude of FAB. It's 300 times 6.5 over 7, which I believe is like 279. 279 pounds. Sweet. So we're just going to put that in 279. Awesome. So now what? Now what's our next equation that we can use? So now we know FAB, we know FAC. We don't know two things. We don't know the magnitude FAD and we don't know W. What if we now take our J components? So we can isolate FAD. We know FAB, we know FAC. W doesn't matter because it's 0 in the J, but if we take the sum of the forces in the Y now, we can find out FAD. So we put FAB in the Y direction, plus FAC in the Y direction, plus FAD in the Y direction, and set that equal to 0. So we know FAD in the Y direction is equal to minus FAB in the Y direction plus FAC in the Y direction. So what is FAB in the Y direction and FAC in the Y direction? Well, FAB in the Y direction is FAB times our Y component, minus 6 over 6.5. And FAC in the Y direction is minus 6/7 times 300. And we have a minus out front. So this is algebra. And when we do that out, we get FAD in the Y direction is 515, and those are pounds. But we got to be careful because what is FAD in the Y direction? FAD in the Y direction is minus 6.5 times FAD. So this is just algebra. If you have questions though, come and see me because it can get confusing. So we know FAD in the Y is 515 pounds. What is FAD? What is the magnitude of FAD? FAD in the Y direction is minus 6 times 6.5 times FAD. So FAD is minus 558 pounds. What does that mean? That means that when we assumed tension, and we always want to assume tension if we don't know and we didn't know. So we said FAD in the Y is a force going from A to D. We get negative, so what that says is our assumption was wrong and it actually looks like that. We have a compressive force. And intuitively, that kind of makes sense. We'll keep it drawn the way we had it just to stay consistent. If we're pulling down, we're compressing this member FAD. So our math corrected our initial assumption, which was tension, and that just says that tension's not right, it's actually compression. All right, so now we know FAD is minus 558. So now we have everything we need to know to solve for W. So let's just do it. Nothing to it, just to do it. So we know that FAB is 279 in the direction of AB. We know FAC is 300 in the direction of AC. We know W goes down in the K direction, minus W in the K. We know FAD now is minus 558 in the direction of AD. So it's opposite, it's DA. But yeah, just staying consistent. If we draw it as AD this way, like we did, we keep that negative. And let's just do that. Otherwise, we can really get confused. So just stay consistent. The math will work itself out. All right. So some of the forces now in the Z direction have to be 0. Some of the forces in the Z direction from, let's say, FAB. So that's 1.5 divided by 6.5 times 279. Some of the force in the Z direction, or the force in the Z direction from FAC, that's 300 times 3/7. Sum of the forces, summing up the Z component of FAD, we have minus 2.5 divided by 6.5 times minus, be careful here, minus 558, and then minus W equals 0. Bring the W to the other side, and then just do the math. 279 times 1.5 divided by 6.5 plus 300 times 3/7 minus 558 times minus 2.5. I always like to just make those positive. What do we get? W equals 407 pounds. So that's how we do it. We break it apart. We look to isolate the components, and we do that by looking for equations that only have the two components if we can. And that's how to do this analysis in 3D. So moments are a bit hard to visualize. So our next step is to do moments. They're a bit hard to visualize, but yeah, try to visualize it in 2D, but you can also rely on math. All right, so with that, I think that's enough for today. We'll talk about this right off the bat come Tuesday's class. That's about it. And in theory, there we go. All right, so I will stop this lecture. Yeah, any questions, ask them on Piazza, bring them by office hours. All right, we'll see you. Have a great weekend.